Hey, what's up, you guys? Westside Wildboy 22 back with another banger. Today's video is going to be going over how to find the characteristic equation of a parallel RLC circuit. So, without further ado, let's get into it. Okay, so hopefully you guys are doing pretty well. I'm doing chilling. It's important to note that the characteristic equation of a parallel RLC circuit is actually different than the parallel equation of the circuit equation, the characteristic equation of a series circuit. So you can just hear how confusing it is even trying to explain what's going on. So I'm kind of making this video just to help myself out too. But it's pretty chill, like it shouldn't be anything too crazy. As far as like, if you have a basic understanding of differential equations, then you should be able to like at least grasp what's going on here. It shouldn't be the first time you've been seeing it, basically is what I'm saying. So let's start. So the first thing we're going to do is actually draw the circuit, because how else are you supposed to know what the heck is going on, right? So let's first start off with a visual aid. So resistor, inductor, capacitor. So we got a circuit like that. So the thing is, it says RLC, so obviously we're going to represent it like such, right? RLC. However, it doesn't actually matter. And the other thing that's important to note is, because this circuit is in parallel, the voltage drop across every single branch is going to be the exact same, okay? So all these voltage drops are equal. We'll call this V sub R. Okay, that's important to know. So let's do a KCL at this top node, okay? So we're gonna have I sub R plus I sub L plus I sub C equals 0. This is very simple. This is Kirchhoff's current law. This is one of the most basic fundamental things in circuits. Okay? That should make sense to you. So the next thing is, we should remember the acronym ELI and the acronym ICE. The acronym ELI tells us the electromotive force is equal to the inductor times the inductance times the current. So that means that V sub L is equal to D over dt times I sub L times L. And that means that the ICE acronym stands for I sub C is equal to C times D over dt times V sub C. But oh wait, I thought that V sub C and V sub L were equal. They are. But I don't know if it's time for some like that. It's a little extreme. There we go. Okay, so now that we have these equations, and we already know that all the voltage drops are equal, then that means exactly what you think it does. That we can basically write an entire equation with these values, and then we can just replace them, like plug and chug. So let's do it. Ready? Okay, so I sub C, nope. You are now, well yeah, I sub C is I sub C. But V sub C can also be put in for right here, so V sub L. You two, my friend, are V sub C now. Okay, now we know what VC equals. So let's rewrite our Kirchhoff's current law. So I sub R, let's just do, instead of that, let's do V sub C divided by R. Okay, that's Ohm's law. That's basic, that's easy, we got that. Ooh. Get the cam right. Oh, it's upside down. Okay, so so the next thing we're gonna do is say plus V sub C over R. I don't like the way that light's reflecting. You can't really see what's going on. Can you? Okay, let's figure this out. All right, that didn't solve the problem completely, but it is better now. Okay, wonderful. So we're gonna write everything in terms of V sub C that we can. So now we have I sub L, that's not going to change, it's going to stay I sub L. Plus I sub C, which we know is C d over dt times V sub C equals 0. Okay, are we following? Any questions? If you can't read what's going on here, I'm just converting everything into basically these constraint equations. And the reason I can do that is because this entire parallel circuit, every voltage drop is going to be the same. So thank you for listening. Okay. All right, sweet. So next what we're going to do is we also know V sub C, and we know V sub C in terms of I sub L. Oh, that's wonderful. Yeah, that's why we did that. So let's do this. So V sub C is going to be L d over dt, right? And then it's going to be 1 over R multiplied by. Okay, so it's actually the lighting's fine. I just saw it. So, okay. So we have this. Let's keep going. Plus I sub L. We'll keep that in terms of I sub L. And then this d over dt was multiplied by I sub L as well. Okay. Then we'll do this plus C times d over dt. And then we'll still VC from up here. So we'll do L times d over dt times I sub L equals 0. Okay. Now that we have this, I think it's pretty easy to see what's going on. I don't want to erase this because I want to reference the circuit later. So we're just going to move over here. Okay. So forget what's going on over here. So basically next what we're going to do is we're just going to rewrite that. Hopefully you remember what it was. Hopefully I remember what it was, but I believe it was V sub C over R, right? And that V sub C is going to be d over dt times I sub L. If I'm not mistaken. Yeah, multiplied by L. Okay, there we go. Then that's going to be plus I sub L. And then plus C times L times d over dt times d over dt times I sub L. Okay, equals 0. This is starting, you might start to say, okay, now I'm starting to see what's going to happen here. And if you don't, that's all right. It's not an intuitive thing, okay? So now let's say, okay, well, these two d's, what happens when you multiply a derivative by a derivative? Well, you get a second order derivative. So let's go d squared over dt squared. Okay, and then we know the coefficient of that is going to be LC, right? I wrote CL here, but LC just sounds better, so let's do LC. Sub L plus L divided by R times d over dt I sub L multiplied by I sub L plus I sub L equals 0. Bingo. Okay, and here's the other thing. When you're dealing with the differential equation, everybody knows you do not want to be dealing with the coefficient in front of the second order differential. So let's get rid of it. Let's divide this whole thing by LC, okay? So let's divide this by LC. Let's divide this by LC. Let's divide this by LC. And we also divide 0 by LC, but we know that anything divided by 0 divided by anything is just 0. So, boom, 0. Sweet. Okay, so what that's going to help us to do is now we can say, okay, well, we got the second order differential, and I don't want to be drawn on diagonal for y'all. The second order differential plus 1 over RC times d over dt times I sub L plus 1 over LC times I sub L equals 0. Okay, so you might say, okay, well, let's pull out I sub L. And heck, you know what? I'd say, hey, you're right. But the problem is, and this is a big problem, if we take out I sub L too early, then the differential equation is going to be messed up. Because we're taking the differential of I sub L. That's the whole point. So we need to figure out what I sub L is, right? It's a variable of most utter importance. Here's what we're going to do. We're going to erase what's up here. Yo, and so I guess that word that was right here was a Fourier transform, which is not the point of this video. But Fourier transforms are really freaking cool. Direct delta functions. Direct delta function. Baby girl. Okay, anywho. So, now we have that differential equation I was talking about, right? So we got d2 squared, d squared over dt squared, I sub L, plus 1 over RC, d over dt times I sub L, plus 1 over LC times I sub L equals 0. I feel like that's a nice place to be. Would you agree? Me too. So I sub L, we are actually told what I sub L is. And we're not told in this equation in particular, we're just told in general, because what we're dealing with here is an oscillatory system, okay? There's pushes and there's tugs on it, right? There's oscillation in the energy because we're dealing with energy storage devices. And in particular, this energy storage device, the current going through that inductor can be defined as a constant A multiplied by e to the power of st. Okay, now why is it this? This is the wave function. This is basically, well, I'll explain it real quick. So what this represents is the fact that I sub L has two components. It has a real component and an imaginary component, okay? There's a thing called the Euler's identity, which is like cosine of x plus I sine of x. So this is just a fancy way of saying that this number, I sub L, could be a real number, it could be a complex number. The idea here is don't think too hard about it. This is what I sub L is, okay? That's another video. But when we take the second order differential of it, what we're gonna get is a s squared e to the st. And the reason why is because when we differentiate that to the first derivative, that's equal to the component of the PEMDAS exponential. It comes down, okay? That's I believe that's the chain rule in calculus. So now we have a times s e to the st, and then when we multiply that by a derivative, now suddenly we get a times s squared e to the st. Okay, that's pretty intuitive, right? That's what I'm saying. Hey, if you've been doing this, you should know what the heck is going on here. Okay, sweet. So we have a s squared e to the st. That's going to be that differential. We got 1 over RC multiplied by a s e to the st plus 1 over LC times a e to the st. And ladies and gentlemen, that's going to all be equal to 0, okay? Then what we're going to do is we're going to say, okay, now let's look and see if there's any common terms. There is a common term that we're going to take out, okay? It's going to be a e to the st, okay? And that's going to leave us with s squared plus 1 over RC times s plus 1 over LC times 1 equals 0. And when we look at this, we say, okay, you know what? One of these has to be equal to 0 for this to equal 0. And let's just go on a limb and say the phasor current, it's probably not going to be 0 in this situation. It's probably not going to be 0 because we know that it's changing. We know that there is a current there, right? That's the whole point of the circuit that we drew earlier, right? There is a current. It's called I sub L, okay? This is what it's equal to, okay? I'm not the person who wrote. My point is this. If we want a non-trivial solution, meaning we actually care about figuring out what I sub L actually is and how it behaves, we need to solve for these constants. So let's do it. Here's how we're going to do that. We're going to say this is not equal to 0. And if that's not equal to 0, then that means that our polynomial characteristic equation is going to be equal to 0. Okay, and that, ladies and gentlemen, is how you find the characteristic equation of an RLC in parallel. Characteristic equation of an RLC circuit in parallel. So let's go back to this one over here. Okay, so this parallel circuit where the voltage drop across every single branch is equal to each other, that characteristic equation actually defines how we find the values, how we find the S value, okay? That's going to lead to other equations. The whole point here is I'm just showing you how to set up the equation to find S. Hey everybody, thank you guys for watching so much. I appreciate you, and I want to turn this into a series. And I think I had a good time. So if you had a good time, please like and follow, and maybe even check out some of my other videos. I do lots of cool stuff.